Hello, welcome to the next installment of our class. And today we will code, we will continue working with our pandemic model, network model of a pandemic, and we will try to model the effect of herd immunity. So we will make it so that eventually we will make it so that some share of the population is immune. And so can it get sick? And we'll see how it will affect our model. And also, so one thing that I want to do this time is to try to model it really carefully, in the sense that so far in all models that we've built in this class, both in the first half that was still in person, and in the second half that we do through these virtual lectures, most of models that we've built were kind of more like proof of concept, in the sense that we would achieve a point when the model kind of works and it produces some sort of result, and maybe we have one plot that illustrates that it kind of works, but we never did a proper analysis. So we never actually used the model for what people actually supposedly use them for, which is to see what is important and what is not important. Like, is it worth, like speaking of last week's topics, which was eliminating the biggest hub. So is it worth canceling big events? For example, what is the expected effect? Do you have to cancel all events to notice something? Like, what happens if you only cancel one event? Is the effect negligible, or is it actually something that may have practical consequences? So this is it would be an example of a question that a model can help to answer. Or another really nice way to use models is when you have two alternatives. So you may do this or you may do that. You may, in case of Lyme disease, for example, you can try to limit the amount of deer, or you can try to well, increase then the number of deer around. And you can try to build a model and see what, or maybe like another option would be to catch mice, right? Put traps that would catch these white feet mice, or whatever the name was, that are mostly responsible, as it turns out, for spreading Lyme disease. So yeah, so you can have two types of intervention, and in real life you would only have money for one of those, and the model can help you to unearth those non-obvious consequences of going with one option or another, because it can, demonstrate you all the sorts of positive feedbacks, negative feedbacks, weird phase transitions, dynamic behavior that is there in the system that we may not feel intuitively, but we can build these intuitions through modeling. So long story short, we really want to do at least once before you do your final projects, we want to have one proper analysis of at least one parameter for at least one output value for at least one model, and that will happen today. But before we do everything else, we also need to add this additional mechanism. We will start with that, which is making it so that the node only stays infected for a limited time. Because so far in our model, when someone is infected, they stay infected forever, they never recover, they never die, they never become immune, so they just go into this infected state and they stay there. And we want to add a little bit more realism to our model. We want it to make so that they stay infected for a while and then they stop being infected. And probably we will make them immune at this point, so they will basically, for the purposes of this model, they will stop being a part of it, kind of, if you think of that, because they no longer spread disease, they no longer can become infected. So it's as if this node got inactivated. All right. So I'll probably make 2 videos, one with the first half and one with the second half, with a short break in the middle. And yeah, let's try that. So I made a new notebook based on the previous notebook that we had. I rewrote the goals. There were 2 cells with some examples, some sample test code that I removed. But let's see what we have. So we have this part where we import modules, and then we have this graph class that I wanted to take out but didn't. We have a test for it. Okay, let's keep it for now. So we have degrees. Should we keep degrees? Degrees calculates the histogram and also plots it of all degrees in the model. Strictly speaking, we won't need it in this particular model, but okay, let's keep them for now. And by the way, I wanted to, for this graph class, I wanted to take it out, if you remember, but and put it into external Python, but a file with py extension as an extension. But for now, I keep it here because last lecture was too long. I didn't want to do it in the end. Okay, we have, what else do we have? We have a random network. A random network is this erdos type network, which we will probably won't need this time because I'm thinking we will stick with Barabasi model for today. But okay, let's keep it. Let's remove the rich club network though, because it's quite unlikely that we'll go back to it. So, and it stays in the previous version of this file, which is from a week ago, which has a name starting with 08. So like, oh, okay, let's remove this part. Let's remove this text. Barabasi creator, this thing we keep. Okay, make this speak a little bit smaller. Okay, let me actually run that all. So I run this, I run this, I run this. Like, let's make this smaller as well. Ew, that's too tiny. Okay, it works. Barabasi works. Remove hub. That was a big part of our work last week, but I'm not planning to use it here, so I will just delete it. But you can go, if you want, in your project, if you want to use this function, you can always recover it from previous week file. Pandemic will be our key function procedure, obviously here. Computational experiment. Okay, let's keep that. So that's what we have for now. So let's start with with point number 1, which is let's make oh no, rich cloud network, pandemic on the rich cloud network. Yeah, so let's make, I deleted this thing, so I have to fix it. Sorry, I keep starting the phrase. Let's start with making it so that each node stays infected for only a limited amount of time, and then it stops being infected. So let's first fix the pandemic thing, instead of, because it's just for the test case, it uses it used to use the rich club network, but let's do the Barabasi network, because why not? Okay, we have it. It was actually kind of easier to troubleshoot on a rich club network, but that's okay. All right, yeah, let's keep it like that. Okay, so what do we want to do? We want to change this pandemic thing. So we talked about that in our Zoom meeting. In order to make nodes infectious for only limited amount of time, we need to track the time that passed since they got infected, right? So we have 3 ways of doing that. Why 3 ways? Because, and for now, for each node, we only keep one value that characterizes it, which is stored in this G values list. This is the list. I think it's a dictionary. Let me go up. Yeah, it's a dictionary because it uses node IDs as keys. So it's in a dictionary. So how do we, and for now, this dictionary only, the values in this dictionary only take basically 2 levels, 0 and 1, where 0 stands for healthy node, and 1 stays for infected and infectious node. But now we want it to be infectious for only a limited amount of time, and then move to a new state, which is like invulnerable, invincible. Okay, how do we do that? We basically have 3 options. One option to extend. Okay, I don't need to write one option. One option to extend the number of states in G values. Let me make it. By using some fancy, or I could have said weird, but I want to stay kind of positive. So some fancy coding scheme, like 0 equals healthy and susceptible as before. 1 to 10 stands for infectious, like 1 to K stands for infectious, infectious, and K plus 1 means immune. And we increase the value at every step once it's above 0. So like the point is here that we could infect them, so shift them from 0 to 1, and then have another loop that goes and checks, or rather in the same loop we would check like if it's 1 or higher, we would just increment it at every time step and count how many days. So basically the value will become how many days ago they had become infectious, and then in the point where we decide what happens to this node, like whether it infects someone or not, which is basically like this line. If the node is infectious, right? So we would have to change this line a little bit. We would have to not just compare it to 1, but it can be anything from 1 to K, but not K plus 1, because K plus 1 would mean a new status, which is immune. And then supposedly to immunize nodes, so to create nodes that are immune from the beginning, that never got sick, we would have to set the value to K plus 1 to begin with. And K becomes the parameter, which is how many days the model remains infectious, right? So that's one option. Option 2, from the programming point of view, is, and you know, it's markdown, so I don't have to write 2 point. I can write 1 point, but it will change it to normal numbers once I'm done. So another option, the second option, is to create another property to give this class graph another property, also a dictionary, to store the time since infection. In this case, value. In this case, G values would remain clear and clean. 0 equals susceptible. 1 means infectious. 2 in this case equals immune. And so it's nice that it would remain clear and clean. So we'll have a clearer dictionary. We won't have this thing that a whole range of values corresponds to actually one state, kind of, right? As we had in the first approach. But the downside, okay, so this is an upside, which is good. But the downside is that we need to mess with the graph class. And why don't we like that? Because it's nice to have a class that's, so imagine this graph class, which I keep for now inside the notebook, but imagine that we have exported it into, so we basically created our module. We took it away, put it in a py file, and now it's a module that we just import. So we want it to be, we want it to stay the same for all of our projects. We don't want to fine-tune it for every project, because that's an easy way to get confused. Because if several of your projects use the same class and you start like adjusting it for each of these projects separately, it's asking for trouble, right? Because your sub-projects may start conflicting with each other. It just makes things more complicated. And we always want to keep it as simple as possible, because we'll have to work with this code, and including potentially in several weeks, a month from now. And yeah, so the easier, the more transparent, and the more modular we keep it, the better. Okay, but so that's what we talked about in the Zoom meeting, but I realized that actually there is a third option, to make values of G values lists. So to make each value of G values to be a list where the 0th element is the state, nice and clean, and the next first element is the time since infection value. So in this approach, to address the state, we'd do something like G values, then ID, and then 0. Does make sense? So it's kind of almost middle ground between the two approaches, because we don't mess with the original class. Still, each node has only one value, which is stored in a dictionary, G values. But each value is now not just a number, but something more complex. For example, a list of 2 elements. In this case, for us, it's enough to have 2 elements. So what should I do? I definitely don't like the option number 2. I don't want that. I'm kind of torn between option number 1 and option number 3. But let's see what else can happen. So option number one would work, but the problem with option number one is, what if we also have like mildly immune, like the person was sick or got their vaccination but never got a booster shot, or they got sick really long ago. And so what if we want to introduce this intermediate state? Because then if we keep everything like encoded in this one value, it can become really confusing, right? 0 is susceptible, 1 to 9 or whatever is like infectious, but then 10 is immune, but then 11 to 20 is mildly immune. You know, it's another it's asking for a problem, right? This first approach would work for these purposes, but it has a huge flaw, and the flaw is that it's not really scalable. Is it? Do you write scalable? Okay, I will write it scalable, like that. So scalable, what do I mean by scalable? If we ever have to add more states for a node, we'd be in trouble. Which means that kind of I'm convinced myself that I'm going with the option 3. I will have each value in these G values will be a list of 2 elements, and the first element will be a nice, clean state. I'm still probably using numbers. Oh, you know what? I can also afford not to use numbers. I can just use basically, I can use strings. It will make it readable. Should I? Will it make it slower? Probably not that much. So for readability purposes, I can even have the first value to be a string. Let's do that actually. And the second value, I mean the 0th and the first officially, right? But the 0th value will be a string, which will make readability so much easier. So I won't actually have to write comments like that if the node is infectious, because this thing will read like G values blah 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 equals infectious. And then you don't need a comment because your code becomes self-evident. And the next value in this list will be a number. In our case, it will be an integer for the number of days since the node was infected. So let's do that. So yeah, one thing that we need to change is I noticed that as I was starting this thing, that when we create a node, when we do the add node, by default the value is equals by default the value is equal to 0 as a default value. And we don't like that, because 0 has a meaning in this in our model. So let's just change this. I think that's pretty much the only change we'll make to the class. We will call it none, which is go to like the best possible value that's not empty but meaningless. So for all, when you really don't know what's going on, is the best default value, the best default state. So it's the best way to create a variable that actually exists, that has a value, but this value is as nothing as possible, none. Okay, so that's one point where we change it. So now, okay, let's, you know what, it's called values, point values, and we're going to change some logic. So let's do Control F and look for point values and just check all parts of our code that mention that. So the graph creator mentions that, good. Add node mentions that, fix that, that's fine. G value 0 equals 1. Oh yeah, so the plotter. So the plotter, now we need to change this part, because now it won't be this. It won't be just values. It will be 0, the first element of values. And let's actually let's actually make it so that if it's 0, then it's blue. We're gonna introduce. Oh, right. I wanted to change it from 0. So if this thing is equals to what? Healthy, then it's blue. Else, so let's change into elif. Self values nodes I 0 equals infectious. And I don't particularly remember what this means, but I'm copying it from here, right? We don't have to fully understand the code in order to update it. If this is the node we're working with, sure, then that's the node we're working with. So if this thing is infectious, it's red. Else, and for now, else will only include these immune nodes. Colors append, say, green. Right? And so green is not defined. So let's define it. Green equals, and these are supposed to be RGB values. Let me add some spaces to make it a little bit more readable. So green is RGB, so it will be no red, quite some green, and let's give it a tint of blue. So let's make it kind of teal a little bit, because we want it to be different from red. I mean, we want it to be colorblind friendly, so it's good to have, if red is warm and only has red, doesn't have any blue in it, then let's add a splash of blue to the green. Right, that's fine, right? That's enough. We can check the color. So let's check the color. Oh yeah, and here we need to change what this thing will be equal to. It will be equal to 1 none. Something like that. Okay, does this work? Nope. Healthy. None object cannot be subscriptable. Oh, right, we ran into an issue. Oh, I should have tested that. So by default, it sets every object to none, which means that we cannot actually do that. We cannot, it's not a list, it's just a none. And so none, the first element of none doesn't exist. So I can obviously fix it here. So the question is it bad or not? If we, in real life, when we run the pandemics, we'll always initialize all values correctly. It's probably okay. Let's just fix it here so that it doesn't bulk at our test case. So if self values nodes I is not none, then all of that happens. Otherwise, because we're creating a list of colors. Else, what's the default color? Also blue? Maybe. Why doesn't it run now? gplot if self values none is not none. Name node is not defined. Nodes. Okay, now it works. Oh, we have a green value. Look at that. Why is it green? It was supposed to be red. Oh yeah, what? Oh yeah, because I sent it to 1 none, but 1 is no longer a value. So it's like 0 will be infectious. So it makes it Yeah, makes it red. Okay, let me check. How do we create nodes? We can, when we create nodes, we can do node and key and value. So let's add an, where is it? Let's add yet another node, which will be like g add node and the number of nodes, like 1, 2. Oh, we already have node number 2. Yeah, okay. Let's then just change it. So node number 0 is red. Node 2 will be like what was immune, supposedly. Right, so this is our blue. Okay, blue is not tealish enough. I don't like this blue. Blue should be more teal. I mean, green is not teal. So green should be a little bit darker and a little bit more bluish. Yeah, that's fine. So these guys, yeah, maybe even bluer. Let's make it like almost 50-50. Yeah, so these, the blue nodes will be susceptible, the red nodes will be infectious, and these teal green nodes, let's actually make it 50-50. No, not 50-50, like that. Yeah, that's good. So these teal nodes will be immune. Good, good, good. So this is done. Let's go further. Where else do we have, where do we address values? So we fixed all of that. We go here, and it's in the pandemic. So when we create node, for nodes, when we create the original network, for node and nodes, so we go through all nodes, g values node equals 0. So first set all nodes to healthy. So instead of setting them to 0, we will be setting them to healthy dot none, right? Then, oh lord, it moves every time. Yeah, I shouldn't do that. So, okay, this is 1, 2, 3, 4, 5. 5 total. G values patient 0 equals 1. So the G values patient 0 element 0 equals infected. The one node is sick. G values node, if G values node 0, part 0, part 0 equals infected, then blah 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 infection happens. For neighbor and neighbors, G values neighbor equals, if G values neighbor equals, okay, so if this neighbor is susceptible, so healthy, and some random coin, then we'll add them to the list of infected, and then for each infected, we go through these nodes and change their 0th element to infected. Right? I think that's how it works. Yep. Oh, wow. Why did they become... Oh, because infected, not infectious. You know, I don't like infectious. I like infected. So let me go back and change. It's a little bit shorter and sounds better. Yep. Okay. Here, where were we? Pandemic. Yeah, okay. So these guys are what? They are infected. Infected means infectious. Now let's make it run for more steps. 7. Oh, the probability is low. 0.5. 3. Okay, 0.2. Okay, sure, 0.1. You can use it. 0.1. No. Well, whatever. No. 0.2. Okay, now we're like, the picture shows the network somewhere in the middle of pandemics. There are still nodes that are healthy and susceptible, and then there are nodes that are infected. So let's now add this second part. So when we make the node infected, and it is this row, we will actually not only reset its status, we will also set the timer to 0. So the value for this node will be infected, 0, which means 0 days since infection. It was infected now, right? So now that's one thing. The second thing, for all nodes that are infectious, we need to increment so we need to count days. And I'm guessing we can do it in this loop, right? Because we have for node in node, so we go through all nodes, if g-values equals infected, and then the whole neighbors thing goes. But before we let the infection propagate, let's update the value. So g-values node, in this case not 0 but 1, we incremented by 1. 1 day had passed, right? We can even write that. 1 more day has passed. One more day since the infection. And if we do it now, why doesn't it work? Oh, because it was none. Why is it none? Oh, right, I know why it is none, because I set it I set it to infected here. So for all healthy nodes, it's set at none. You know what? Let's set it at 0 for all nodes. So none of the nodes has it as none. Even the healthy nodes that were not infected yet will have the second value as 0. The benefit of having it as none is that we can cause errors every now and then, and we can spot places where something is weird. But the benefit of having a 0 is that we're less likely to have these errors. It's kind of silly what I said, but it's kind of not. So there is a benefit sometimes in making a code generate errors when the code refuses to run when you have an error in logic, right? Because if you make your code really flexible, sometimes it would tolerate abuse, and when your logic is incorrect, it will still run, but it will give you wrong results. So from the logical point of view, the healthy node doesn't have any time that passed since it was infected, because it wasn't infected yet. So if we write none here, then if later we become, for some reason, confused and try to access this value for a healthy node, we would run into a problem, and we will notice that. But whatever, let's keep it at 0. Okay, so it works. It works. We can also look what sits in G values. Node 0 is healthy, node 1 is infected, 2 days had passed. Node 11, look at that, was infected for 4 days now. So yeah, it seems to be working, right? Some nodes are healthy, some nodes are infected. Those nodes that are infected, some of them have non-zero a number of days that they were infected. So now we need to add this limit on the number of days that they stay infected, right? So let's do that. How do we call that? What's the official name for that? So the official name for that is, I think it's called period of infectivity or something. And that's just a horribly long phrase. Oh, look at that. In the United Kingdom, at least, it's called period of communicability, which is even worse. Also known as the infectious period. Infectious period is better, but still too long. So how will we call this variable? inf period, infectious period. It's okay, let's keep it long. Infectious period. So infect period, and the default value is, we should either put something, 3 options, well, 4 options: none, something really small, something really large, something realistic. Let's have it at something really large, I guess. 100. No, that's stupid. Let's keep it at 1, which is whatever. Infect period. So the default value is 1. But so here we will do infect period equals also 1 in the test. This is the test case, right? Test case. So infectious period will be 1. What does it mean? It means that you are infectious for 1 day. So let's look at the code. So once you're infectious for 2 days, you're no longer infectious. Once you were infected 2 days ago, you're no longer infectious. So let's see. We either put this thing before that or after that. So let's put it, I guess, before that. So what's happening? If G values node, the number of days since infection, which is 1, if it is equal or larger, but equal would be enough. If it's equal, okay, let's write equal. If it's equal to this value, then we will do something. Let's check the logic. So when it's born, it's set at 0. So when it's born, either here, up here, when we infect the first node, it's set at 0. You know what? Let's change this row. Let's just set the entire value to infected, 0. Otherwise, it's annoying. So the entire thingy changes to infected, 0. So when we infect the first patient, its number of days since infection is set at 0. Same here. When we infect new patients, the time since last infection is set to 0. So on the next run of the loop, it will be equal to 0. And then here it will be changed to 1. Right? Which means that if infectious period is equal to 1, then the first time, so the next run of the loop after they were infected, this will be false and everything else will happen. But then their time since infection will be immediately switched from 0 to 1, and so on the next run of the loop, this will be true, and we can inactivate them. So the logic seems to be working. If we check before we update, then we should just compare with the infectious period itself, because the first time around it will be 0, it will run, and then the next time it will inactivate. And the same applies to infectious period of like 3. If it's 3, then it will be 0, increased, 1, still runs, increased, 2, still runs, increased, 3, next time it doesn't run, right? So it will run for 3 times. Okay, so what we need to do here is inactivate the node and then also skip everything below. So inactivate the node. G values node 0, values node 0, which is the status. We don't care about the time anymore. We just want to inactivate it. It is now immune. And now we skip the rest. And how to skip the rest? We just need to skip everything for this node, right? So we're in the loop. This is the loop, the closest loop to us. So we just break from this loop. So we write here break. No, don't break, continue. Right? What continue does, it skips the rest of the loop and then goes on the next run of the loop. You know what? Let's do else. It's the same effect. It's just the result will be the same. It will just write. I mean, it will read easier. Continue is a little bit maybe dangerous sometimes because it's easier to get confused. So let's keep it crystal clear. So it's just if else. If the node is like too old, inactivate it, else do everything that you need to do with it, starting from making it 1 day older. Okay, are we done? Does it run? Yep. Nope. Or maybe it does. Because sometimes it's more than one infectious node, like here. Okay, I think we need to increase the probability. Nope. Okay, maybe it doesn't run. What did I do wrong? Why are all of them immune? We never had red nodes anymore. Healthy infected. Okay, infect period 5. Okay, so it does work. Was everything that I said before wrong? So it seems that with one... Why don't we never catch... Oh, no, we do. How does that work? Okay, you know what? Let's make a nice test case, by the way. So I run for 7 steps, sure. So let's just make a test case nicer. Let's show all stages of infection propagation. For I in range like 10, no 8, in range 8. We don't care about history. We will do only one step. Oh, we cannot do that, right? So what I wanted to do is to run like steps of pandemics, but currently my function doesn't. So run one step plotted, another step plotted, another step plotted, but right now my function doesn't support that. Because it reinitializes the states all the time. Okay, let's just fix it. So let's add like ray init equals true. By default, ray init is equals to true. Ray initialize. Let's go with the full name. So if ray initialize, then we do this whole thing with setting all nodes to healthy and setting patient's node to 0. But if not, then we don't do this thing. So, and here we'll add if I equals 0, run that, else, run this, oops, run this, but do ray initialize equals false. And then we will need a figure, plt, figure fig size equals like wide, like 12 by 6. And we will do subplot, plt subplot, and I use like 8. I go range to 8, so it will be like 4 by 2, or 2 by 4, so 2 for I plus 1, I believe. because it uses like subplot, and like everything else uses one indexing rather than zero indexing. Will it work? Okay, it works. So look, we don't see, because the way I build it, we don't see the first, like we don't see the original network, the network that's all healthy and only seeded with 1 point. The first time we look at it is either it ran for 1 step. So this is actually not the original state. This is the state after it ran for 1 step. But after that, each next one is the next step. You know what? We can probably do something like PLT title I. Nope. Oh, of course, I put it in quotation marks. I want I itself. Yay, look at that. That's neat. And that's a neat way to troubleshoot stuff. Like, I really like troubleshooting visually, which is maybe not even the best practice, but it definitely works for me. Okay, so here's what happens. Here's why that's why in some cases, oh, that's awesome actually. That's why before, when I just kept rerunning it again and again, I wouldn't see red points quite often. And that's because red points are around early on, but then what happens when the node stops being infectious? It becomes immune, which means that infection can get trapped, right? If both nodes to which the infectious node is connected got immune, then this infectious node, I mean, yeah, if imagine that some nodes are connections, they infected another node, but if this node is not connected to any other node, if like, I'm not sure what I'm trying to say. Anyways, node that stopped being infectious become immune, which means that the disease cannot propagate through it, which means that as we go on, the network becomes less and less susceptible for the disease with every step, right? And so the disease just runs out in many cases. And we can rerun it. Yep. And we can rerun it. And we can rerun it. I want at least one case where, yeah, whatever. I wanted one case where the red node would have survived until later, but no, it doesn't. It happens very rarely with this set of settings, right? But of course, if we change infectious period to 10, like let's do that. If we change this value to 10, now they stay infectious forever and everyone will get infectious, right? If we set infectious period to 7, like to 6, then probably everyone will get infected, but some will already be immune by the end. But as you can see, nobody was spared. It ran its way, but all nodes got infected. But with situations when the disease is like really fast, in the sense that people quickly develop immunity, then we have this nice feature that it does not necessarily infect all nodes in the population, right? So that's pretty. And I like my teal color. I think it's a good color. It's like publication appropriate. I'm very modest. Okay. Good. Good. So how to model herd immunity? Well, now it's obvious, right? Isn't it? We just need to write another function that would, or add another parameter here that when we create the state, when we initialize the model for the purposes of pandemic, we don't set all nodes to 0. We set some of them to 0 and some of them, I mean, not all nodes to healthy. We set some of them to healthy and some of them to immune. And we'll have the same effect as, so it will be like as if we arrived at this stage, like stage 6 to stage 7. So we'll have a mix of susceptible nodes, blue nodes, and immune nodes, which are teal nodes in this representation. So we can totally do that. Okay, let's do that. Do we want a new function? Probably not. Let's give it here. Let's incorporate it into this pandemic function. Pandemic as a function gets kind of more and more variables, but that's okay, I guess, for now. So infectious period, vaccination rate, vax rate, and by default it's 0, right? No one is vaccinated. But let's change that, and so in our test, let's set vaccination rate to like 0.1, 0.2, so small share but some share. And we don't have to change it here because the vax rate will only matter when we initialize the network. So once we stop initializing it, we don't have to communicate this variable anymore. But vax rate, so here we need to toss a coin. We have a coin tosser somewhere here, right? This one. So I can just see, I try to avoid thinking as much as I can. I already have it, like something where uniform probability is compared with the probability level. So I'll just copy this thing and adjust it. So if this thingy, except it's not like with probability anymore, but with vax rate. So if a randomly chosen uniform value falls below vaccination rate, which is like a less likely event to happen, vaccination rate is like 0.2. So this means that it was actually vaccinated. We will set it to immune, else to healthy. So immune. Right? The word healthy does not quite represent the situation anymore. It's actually susceptible. So, but I think healthy, like, let's keep it 4 just because. Okay, so now it should run. Presumably it's enough. Yay! As you can see, it seems to be working because now, even when we created the network, some nodes were immune, even early on, right? Okay, let's make, just to have a nice picture, let's lower the vaccination rate. Yay. Good. 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 Awesome. Nice. So I think at this point we fulfilled 2 first points of my program. We made it so we implemented this thing that Sasha proposed, which was let's keep nodes, let's allow them to stay infected for only limited amount of time, and we added vaccination. So the next step to do would be to study the effects of vaccination properly. And it's not a small undertaking. So I will stop the recording for a few minutes. And then in like 5 minutes, I will return to the stream as well. And I will do this second half. Okay? Yay!